I realize we have 1 minute until it officially starts, so I'll randomly ask you. It's been a good week-ish. So, are people now feeling calmer, like know what's going on? Or just now it's more stressful? Both? It's possible to have people. Glad you're here. I hope this weekend is pleasant for you all. But I realize it's not going to be like normal because you're like, I'll hang out with you, but back, like, Phil, whomever. Right? Speaking of like Phil, I know I nag, but there are at least 3 people in this class who have some health concerns that I have got to make you gotta keep your masks over, okay? So I realize you're probably cool, but there are at least 3 people who it's a concern if you aren't and you're breathing on them, okay? I don't want anybody to feel scared. I mean, feel free to like panic in general about the safe things, but not more scared than normal, okay? Sweet. All right, today we've got chemistry and bonds, and it's gonna be cool, I think. I like this part, at least at this level of stuff. People in chemistry class, you can't tell Dr. Moore that I assign personalities to molecules, okay? Like, that's deeply what you're not supposed to do, but they are kind of cute. We're gonna go over some basic concepts really fast. Your book covers them in a lot more detail, and I know in chemistry you can go into a lot more detail too. But this is gonna get us up to speed with like what's happening in the biology part. So with that, today we're going to talk about chemicals a little bit. We're going to spend most of the day talking about bonds. And then there's a quiz, which is like open book, open paper, open me today, not normally. It's also online if you want to leave at the end. You can go and do it online, or you can do it here in class. All right. Before we get started, iron's an element, right? And like, there's iron in your breakfast cereal, hopefully. But then there's also like iron in, say, cars and paper clips, right? Tell me about the properties of iron. Is it magnetic? Like if you pick up pick a paper clip with a magnet, okay? Does it rust? Yeah. It can like move a charge along through it, right? You could, if it gets zapped by lightning, it'll move the electricity along. Okay, so iron's element's great. It shows up in like, cars. Iron's also in vitamins, right? But it's not the same kind of iron. Right? People are like, no, like not eating the paper clips. Somebody, Noel, right? Yes. Can you tell the class? So this is a magnet, and it washed off. Any like stuff on it? Okay, so there's a little bit of fluff on it because they're really strong magnets, and I stuck them together on like a piece of paper, and I can't pull them apart now. I need something else to get this done, but there's nothing on this, right? Just plain. Do we believe Noel? She seems trustworthy, right? Okay, yeah, great. If I please do. Okay. Is there prenatal vitamin? I'm not pregnant, by the way. I was, but I'm not. Just in case you're like, this is how she tells people that. I have all sorts of these. And I should have brought a hammer, but it's Friday and it's hard for some of us to remember things. Like, I remember to bring these. Not remember to bring a hammer. Okay, so nothing in the bag besides vitamins. I just wash them. I can break stuff. Okay. Cool. So some vitamins, vitamin. Wait for it. Okay, this is Mackenzie, right?
Yes.
Do you think Mackenzie's trustworthy too? Oh yeah, well, class likes you. Normally I'd hand this all the way around, but I don't want to hand it across a lot of people. Mackenzie? What's on that?
ring of something.
Yeah, like little tiny fluff bits of something, right?
What you doing?
What color is it?
Red?
Yeah, like rust color maybe?
Yeah.
And it's stuck? The just regular boring vitamin powder is like this weird grayish color. But there's, I don't know if you can see it, there's a red, little tiny red flakes all over this. That's sticking to it, it's not falling off. So like, they do back, right? So you get just the regular rest of the powder and like put it on, right? It falls off. But these ones aren't falling off, they're sticking to my magnet. Why are they sticking to my magnet? Because it's iron, right? It is the same stuff, paper clips are made. It's an element, right? Iron's an element. The rules that iron follows has to follow the rules. So iron's magnetic. I realize iron can come in different colors, but that rust color, it's there. It's pull outable. If you have nothing else to do this weekend, or anytime, if you get a magnet and breakfast cereal, you can squish up a breakfast cereal like really well. It helps if you have gross breakfast cereal like bran flakes or something. If you got like fruit puffs or whatever, you're probably not getting much iron out. But if it's like the kind of cereal, if you got like grape nuts, does anybody here like grape nuts? Have you ever had them? It's like eating cardboard. Oh my goodness. Anyway, but if you get an iron-rich cereal, you can squish it up with magnet, and then you can pull out some iron. It's the same iron. The point being, elements do elements retain their identity as who they are, what they are. Okay, they show up in different forms. They look different, like right if you're in a car, if you're in a vitamin. But the rules the element follows, the fundamental chemical identity of the element, to the level of atom. An atom retains, just remember this, it's going to be on the quiz. An atom retains its idea, its fundamental identity as an element, okay? With me there? Sweet. Okay. Now, atoms are cool, they're nice. Let me make sure this is recording. Yeah. Okay. They retain their identity, they're cool, but there's not that much you can do with just an atom. They're way more interesting when they're stuck together into complex things. Stick some atoms together, you get a molecule. They're stuck together by chemical attraction, a chemical bond. We're going to talk about 3 types, well 4 types. Briefly, this is the part that there's many parts of this class that I'm like briefly glossing over lots of things, but this is okay. In chemistry, I know you're going to talk about this more. And if you're not in chemistry, that's cool. This is what you need to know for this class. One of the most important, probably the most important type of bond for biology is what's called a covalent bond. Okay? Covalent meaning both of them, both atoms are participating, and valent meaning they're sharing valence electrons. What that means, as normal people talk, is let's say you've got hydrogen atoms up here. Hydrogen atom, the little pink ball is showing the nucleus, it's showing there's a positive charge there. And the little yellow fuzzy bits outside is showing, you know what? The electrons, they're kind of spread out around that charge. It's shown like a fuzzy cloud because of probabilistic electron density. All you're saying is basically the blob of negativeness is around that. Okay? There's another hydrogen atom over here. It also has a blob of electron density around it. Cool? In biology and chemistry, just in the universe, positives and negatives attract. So opposites attract. Alright? A positive sticks to negative. So we've got these 2 hydrogen atoms here. So far so good. If you make them close to each other, the negative electron, so the electron density here, it feels this positive, but it also feels this positive. And because there's room around the hydrogen atom for one more electron, there's room for it. The electrons will go go from here to here, but kind of just hang out around both. Alright? So these are now pulled together because electrons are being shared between both of them. Does that idea make sense? So now they're stuck together. This bond right here is called a covalent bond. It's going to be when pairs of electrons are shared across two atoms. Now, these two atoms are now attached. And they're attached in the same way, I mean not in the exact way, but like your finger is attached to your palm, right? It's attached. Technically it can come off. If it comes off, there's been a dramatic change in your day, right? Okay? These two, when there's a covalent bond, you need to use a chemical reaction to break it, okay? You can't just like shake it hard. You need to have a chemical reaction to break that bond, okay? With me on this one? Covalent bonds. In biology and everywhere, in chemistry, you'll see it drawn as a line often, just a solid line. Come on, stick freeze it in. Okay. You'll see it drawn a couple of ways. You'll see it drawn as a solid line. You'll see it drawn something like this, where you've got these little electrons being shared between things. You can see it drawn with little dots. You can see it just in like pictures. But probably the most standard is this one. Now, for exciting chemistry reasons that have everything to do with the shape of the atom and the number of electrons it has, different atoms get to make different number of covalent bonds. So hydrogen gets one. Hydrogen can stick to one, can make one covalent bond. That's it. Okay? It can make a covalent bond with lots of different things. It can make a covalent bond with oxygen, with carbon, with another hydrogen. But it only gets to make one bond. Alright? Oxygen gets to make two. Alright, so here we have oxygen with a double bond, another oxygen. And he's one of those creepy, like, pointer sticks. You know what I'm talking about? Like a big stick. Makes teachers look impressive, not really, but I'm sure. Okay, so you can have oxygen, it makes two covalent bonds, it can have two covalent bonds itself, it can have, over here, oxygen, this oxygen has a covalent bond to hydrogen, oxygen to hydrogen, right? Oxygen making these two bonds. How many is this hydrogen making? Just one, and that's okay, the rules are fine. Is it there? Carbon makes four. So carbon can do all sorts of stuff. So carbon has something like this, where carbon, you've got bonds to hydrogen. You can have carbon with a double bond out to oxygen, and then two hydrogens over here. You can rearrange these lots of ways, but hydrogen thing one, oxygen two, carbon four. This is going to come up later. So far, so good? Questions about this? Just for the record, and you probably know this, you've probably heard people say this before. If you have a question, but you like see the rest of your classmates doing the nod thing, some of them probably have the question too, but they're like, I think I'm supposed to know it because everybody else is nodding, which is a weird feeling. It's a weird feeling to be in the class and like, I think everybody else understands it. Actually, one time, just goodbye, in class, and I have no idea what's happening, like none whatsoever. And afterwards, I asked the prof, I'm like, hey, I don't know what's happening. He's like, no, blah, 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 blah. The next class like, comes back, he's like, everybody in this class asked me the same question. Guess it all emailed him. So we're going to do it again. It wasn't just me. Right, so do ask questions. Speaking of questions that like, a lot of people are like, this is obvious, and other people are like, whoa. The naming conventions sometimes throw people off, okay? So you all are solid on the names of the elements, right? So like, when you see this O, you know it's what? Oxygen? Sweet, people are really so ready to twist it. You know it's oxygen. That's not the tricky part. The tricky part is normally when people talk, they're like, I don't know, if you're supposed to pick something up at the store, you'd be like, okay, I'm gonna pick up, I don't know, what are you buying at the store? Help me out. I ran out of ideas.
Dr. Pepper.
Dr. Pepper and
Apples.
I say what?
Bread.
Bread, like a healthy breakfast. Kind of, it's good. So you bread, Dr. Pepper and bread, right? It's normally you'd be like, I want Dr. Pepper and I know 3 loaves of bread, right? Which means sometimes people get confused because that's how people talk, right? People say the thing and then usually they say the number of stuff they want first and the thing. So there have been so many students who I've seen who've done something like this. They see water and they're like, ah, I have hydrogen and then 2 oxygens. Which makes sense with how you talk, but is there something very, very wrong with that? Somebody in the back is nodding enthusiastically. What's wrong with that?
It's 2 hydrogen, 1 oxygen.
It's 2 hydrogens, 1 oxygen, okay? So the way this goes is this little subscript number, the little one, that's pegged on to this first one. So if it's H2O, it's hydrogen, 2 of them oxygen. Okay? So with this carbon, hydrogen, 4 of them. Okay? So if you ever draw water like this, OOH, you are getting that wrong. It does not have 2 oxygens. It's H, 2 of them, O. Okay? With me there? Subscript belongs to the element here, which if you see it, where it's the last one's obvious, because like, well, yeah, there's nothing else it could be. In cases like this where it's this one, that 2 has to be the height. Cool? Did I beat this concept too much? Okay, you're like, yeah, we get it. Okay. Great. So back up here with these bonds, there's a pair of what I call valence electrons. There's a pair of electrons right here that are shared between these, right? This hydrogen is now associated with this carbon. They're sharing a pair of electrons. It's great. Cool. They're stuck together. It's a molecule. Somebody from this half of the room, do you have a cousin? Cousins are particularly bad about this. One of them. Cousins are great. They're fantastic. But you have a cousin that is about your age, probably a little bit older, and or it can be a friend. And when they share, but their piece of cake is always bigger. Do you know this person? Are you this person? Okay, you know this person, right? Like, they're sharing, but it's not 50-50. You've known this person? Okay. At the risk of personifying these elements, some elements share better than others. So, some elements really are greedy. They really like electrons. They have electrons they need, but they want more. They're very greedy. Oxygen is a greedy element. Some elements like hydrogen aren't quite so greedy. They're like, yeah, you know, I'm like not that emotionally attached to my electrons. Okay? This arrow here on KR table basically starting bottom left going to top right shows the general trend, what's called electronegativity, which is just a way of saying how much this atom wants to hog electrons. So, atoms over here, elements over here, aren't that greedy about electrons. As you move up and to the right, typically they hog more electrons. Okay? There are specific chemical reasons why, and there are a few exceptions here, but in general, and for our purposes, this trend's right there. So then when you have something like water, you've got oxygens, 2 hydrogens. Oxygens over here in the periodic table, hydrogen over here. Hydrogen doesn't hold on to its electrons all that great, and oxygen's super greedy. So what happens is, you've got a covalent bond here, they're sharing electrons, but oxygen's pulling more. With me? So still sharing, this is a picture that shows that. So these little white specks are where electrons can be in places. You'll see electrons will be over here, they'll be over here, they'll go back over here, because they're being pulled towards the oxygen more. Definitely both places, the oxygen's tugging forward. Which means, you see this little squiggly symbol? It means partial. It's drawn like this. It's actually partial, but it means partial. So what this is showing is to say, you know what? This thing right here, the whole molecule is neutral. Okay? But there's a partial negative over here because oxygen is pulling some of the electron density away from hydrogen. Which means over here, hydrogen over here, and hydrogen over here, they're a little bit positive. Okay? On this particle. So far, so good? This is called a polar covalent bond. It's polar. So when I think of polar, I think of like north and south poles. Or two penguins. When you talk about a bond being polar, does that mean it's cold? Is that what we're trying to go for? Does it mean it's far away? Help me out then. Why would you call it polar? If it's not cold, if it's not far away, it's not penguin-like. It doesn't mean penguin-like. Okay. Yeah. Remind me of your name?
Raven.
Raven? Raven? You say it's a polar bond. What's that mean?
It's negative.
Doesn't have to be negative though. Well, so you got part of the idea that part of it's going to be slightly negative, but another part is going to be slightly positive, right? So that idea is totally getting at it. That there's going to be a difference there. Anybody else want to take a shot at it? She's got the idea that like there's something different about one side than the other. Okay. So that's where the polar is actually coming from. It's supposed to be ends, like the pole of the Earth, like different ends. But as Raven points out, the ends are different. You've got a negative on this end, you've got a positive on this end. The ends are different. Okay, so polar bond is not symmetrical. Okay? In a sense, we'll see this later, okay? We're gonna come back to that. So you've got covalent bonds, which is bonds in a molecule. So you've got several atoms. When they're stuck together with covalent bonds, they're a molecule. Okay? In that molecule, this covalent bond can either be non-polar, it can share equally. So like, go back here. Hydrogen sharing with hydrogen, they both pull equally. That bond is non-polar. Neither hydrogen gets to grab more because each hydrogen, they're identical to each other. Alright? But in something like water, you've got a covalent bond, still a covalent bond, but it's polar. It's a polar covalent bond where oxygen's probably more. Okay? Well, you can imagine with certain elements tugging harder, you could imagine some of them pull really hard, right? So this side of the class has a buddy or cousin or friend or somebody who doesn't share super well. This side of the class, did you know that mean little kid on the playground who, when you're trying to share with them, they just grab it? You know this person, you're like, hey, right? Or you're like, shove, whatever this you designate with. In chemistry, there's no personality, but sometimes that sharing ends up just taking. So you got sodium, a sodium atom. This electron here is not being held that tightly by sodium. Yes, sodium has it. This whole thing's neutral, but this electron, it's not that tightly held. All right. It's all by itself, floats them out into this orbital. Chlorine over here, though, also neutral. Both these are neutral, right? They have equal positive charges and negative charges. They're neutral. This is neutral. Chlorine, though, desperately wants another electron. Nothing would make it happier in life to have an electron. It's got a spot for it right here. Like, I could fit it in. It would be perfect. It'd fit right here with have a friend. Okay? So when sodium gets next to chlorine, chlorine's like, hey, I see an electron. Sorry, chlorine sees a sodium has an electron. And it's like, yeah, sure, whatever. And chlorine's like, I want. So they get closer together. this electron gets ripped completely off. It ends up living over here. Okay? So it's kind of like a polar covalent bond, except it's taken all the way. They're not even pretending to share electrons between the two of them. Fair enough? So what happens then, this happens. Now, sodium gave up an electron. It got rid of it. Goodbye. Gave up an electron. But now it's positive. Normally when I give up something, I think about being negative, right? Like, I gave it up, I have less. How come sodium gives it up, but now sodium's positive?
It lost a negative charge.
Lost negative charge. What? No, right? Atom, sorry.
Yes.
Atom. It lost a negative charge, okay? We're with me here? So it lost a negative charge, so now it's positive. Similarly over here, chloride, it got a negative charge, so now it's negative. Everyone's good at this concept? Okay, so now the next step of this, and it's kind of a complicated process, many steps. Sodium, okay, gives up here, punches here, but now the sodium ion, it's an ion because it's now charged. Back here it's just an atom. Over here it's now an ion because it's charged. Positive or negative works fine. It's an ion. Now there's a positive charge here. Positive charge here and negative charge here. Opposites attract, right? In chemistry. So now this ion and this ion stick together. They're not sharing electrons. They're not a molecule. They're salt actually, but they have what's called an ionic bond. Okay? They're stuck together, but they're stuck together like holding hands with somebody sticking together. Okay? Meaning, yeah, that's decently strong, but you can come apart without like breaking bones. Okay? Everyone's with me here? So like table salt is probably the example you're most familiar with. And it's decently strong, right? Like you can see table salt, you can look at it and be like, oh, it's stuck together. It's stuck together with ionic bonds. It's this. It's sodium chloride. Stuck together. You put it under water, it'll associate, but they'll still be sort of close together. Everyone's cool with me here? Great. Here's the picture of if you're trying to visualize where are my electrons going to be? Non-polar covalent bond, evenly distributed. These are held together, they're in the same molecule. Over here, ionic bond, this little part has completely given up an electron. This part totally got an electron, now they're stuck, they're associated, but they're not a molecule, they've got an ionic bond. Non-polar covalent bond, ionic bond, polar covalent bond basically halfway between these two. Still covalent bond, these are still definitely a molecule. Partial positive charge, partial negative charge. Everyone's good? Sweet. There's one more kind of force or association to talk about, and it's the weakest association that we've got, but it's still good. Before we talk about it, does anybody have a gecko? Or had a gecko as a child? Yeah? Sweet. Was it cool? Thanks. Could your gecko walk up the glass? Sometimes you're like, if it was motivated enough? Okay. Sorry, this might not like really little. But was your gecko's feet sticky like glue? Yeah, not like when they stick, right? Like after you touch them, it's like a little bit sticky. You mind giving me a name?
Easton.
Easton, okay. So Easton's gecko. There's other people who've played with geckos. And they're kind of cool, right? Like, whoa. Okay. So their feet stick to glass, but like, not like tape, right? See this? Like if you stick it, there's not like glue that comes off for you. Okay. Geckos and other things, everything, has certain attractions called van der Waals interactions, and it really looks like there's a W there. It is, but this guy was German, so it's buff. Anyways, van der Waals interactions are forces. What that means is there are transient attractions that happen between the molecules just because nature's kind of random, a little bit. And this is a weak attraction just because of proximity. And you at a much larger scale, might have this same thing happen to you. Have you ever like had familiar strangers? So every morning at 8:47, you pass the same person. You're going this way, they're going that way. You have no idea who they are, but like after a while, if they're not there, you're like, I hope they're okay, right? You don't have any like real attraction to them, but there's a slight attraction by being in the same place, same time. Okay? Molecules have a similar thing that happens. By next week, I'm going to figure out how to raise and lower this without like smoke coming out of this. Nope. But for now, can you see this tiny little chunk? Plastics, okay? Where's my chalk? Oh, here it is. You've got some molecule. Its electron density spread all over the place. The electrons hanging around. It's neutral. These electrons move around. For a brief moment in time, just because they're moving around, you might get a transient partial charge. So let's say you get a transient partial positive charge. For a brief moment in time, there's a little bit more electron density up here. Partial negative, partial positive. Okay? It happens. It's moving around. It's really fast. Okay? Well, if you've got this molecule that only has 3 partial positive, something like water is always a partially negative of an oxygen, partially positive by hydrogen. This is just fast. Okay? You've got this molecule. If you've got this molecule that's just next to it, if there's a brief partial positive here, the electron density over here is like, oh hey, there's a partial positive. So a little bit more of electron density goes over here. So now I have a partial negative over here. Because it's responding to this quickly. And now there's a partial positive over here. You see how that works? This is not that strong. It's super transient, but they just kind of are associated to each other. Alright? You might have seen this like with Cheerios floating in a bowl. I'm stuck in breakfast cereal. I can have breakfast, but maybe not enough. Like the Cheerios just like hang out next to each other. Right? Okay. That kind of idea here. Super brief, super transient, but if you get enough of them and you're set up properly, it actually can be quite powerful. And that's the force that's holding geckos on the wall. They've got a lot of surface area on their little patty feet. It's ridged in a nice way. And they can stick it up to glass, and those transient interactions between their feet pads and the glass can hold them off. Technically, if you touch glass, you have slight transient interactions too, but relative to your body weight and how much surface area you have in your hands, you can't like Spider-Man up glass. If you can,